Hello, everyone. Thanks for tuning in. Let's get started. I'm Ben Baker from Juniper Networks, and I'm here to talk about what nature can tell us about IoT security. So it's been about 3 years since we first developed this concept of the self-driving network, and clearly it's an analogy to self-driving cars. And we have a lot of what I think is very interesting material that you can search for on the web on the history of the development of the automobile and technology, and more recently self-driving vehicle technology, and using this to think about advancements in networking technology and the social and economic implications. But anyway, our premise is that if you dig into the numbers, you find that for network operators, the ratio of OpEx to CapEx is about 4 to 1. So the cost to operate a network is much higher than the cost to initially build out a network. And as traffic continues to explode, networks are becoming increasingly complex, difficult to manage and to operate and to secure. So the self-driving network will be more operationally efficient, secure, reliable, resilient. And technologies like SDN, NFV have been incredibly useful, but they haven't fully addressed these challenges, and we've joked that the self-driving network is the new SDN. And the self-driving network, just briefly, is a framework around the progression of several different technology areas. First, streaming real-time telemetry. Seconds matter now, so intermittent polling isn't good enough, and the idea is to collect the data and intelligently present it to Juniper systems or third-party systems for analysis, and open standards like OpenNTI, OpenConfig, gRPC are important here. Next area, automation. So moving from human-driven scripting to more holistic workflow automation that integrates application development and networking. So progressing to event-driven networking and toward autonomous networks. And I don't think we ever fully get to autonomous networks, but it is a good goal to shoot for, I think. Next area, intent-driven. So tell the network what you want to accomplish, that end-user intent or the application intent, and not exactly how you want to get it done. And then the network configurations automatically follow this guidance. Next area, multimodal views. So correlate data sources across geographies, across time, across different network domains to get the full picture. Zoom in on trouble spots for granular analysis, and then zoom out when the problem is resolved. So let's say you see a spike in network traffic. Is everyone rushing to download the latest Lady Gaga song, or did someone just score a great goal in the World Cup, or is it a DDoS attack? And if you can correlate different sources of information, it helps you figure this out, and obviously the action you take is going to be very different depending on what's going on. You know, you're going to either open up new bandwidth or the opposite, shut a port down. And I think you can imagine, maybe one day we'll get to the point where you're scraping Twitter feeds, for example, as another source of data to feed into that network monitoring and decision-making process. Final area, rules-based systems versus machine learning. I'll get into this a little bit more, and I definitely don't think it's an either-or. We do need both. And ultimately, the idea here with a self-driving network is to simplify network operations, reduce human error, augment human operators to free them up to do higher-level activities. So the self-driving network will self-configure, self-correct, self-fill in the blank, and getting more to the topic of today, it'll self-defend. And by the way, if you're keeping score at home, this is another SDN, the self-defending network. I think that's all I got, just two of them. And there's a lot at stake. We've all heard the scare stories about IoT security breaches, some of them real, some of them, I think, more imaginative. One that I'll point out here, several months ago, the big news was the discovery of these malicious chips that had been inserted directly onto motherboards of servers sold by Supermicro. And this was at the origin at the factory in China where they're assembled. And what we've been hearing from the threat researchers is that they were able to discover this issue based on unusual communication behavior from the motherboards. And this is an important point. So security policy, networking policy didn't catch the problem. It was behavioral analysis. Now, today, I want to introduce a new analogy to help us think about IoT security, and that is this idea of categories of IoT devices as flocks of birds. So most IoT devices are flawed, but in ways not like humans. They're simple, dumb, often single-minded with a defined purpose. But I guess now that I think about that those words do refer to some humans. But IoT devices, they should generally be predictable. But a problem is that IoT devices often hide behind gateways, roaming agreements. Their traffic can be encrypted. They might not have well-known, established signatures or trusted IDs that the network knows. So just fundamentally, visibility is an issue here. And then with the approaching phenomenon of massive IoT that 5G promises to bring, there's just too many devices and too many types of devices on the network to manage manually. So the scale and the complexity of the problem is overwhelming any current approach that might only be if-then or rules-based. So all this points to behavioral analysis as a key part of solving the IoT security problem. So IoT devices of the same type, whether it's thermostats, cars, baby monitors, elevators, whatever, behave in similar ways like flocks of birds. They rarely deviate, but when they do, usually all of that same category deviates. And we can use cluster analysis to help solve this problem. And to put this in the context of the artificial intelligence buzzword landscape, cluster analysis is a form of unsupervised machine learning. So I'll talk about that a little bit more. And then we can also use classification algorithms, and classification is a type of weak supervised machine learning. So we can use classification to determine these different flocks or group of devices, exactly what the devices are. Now, the math and the techniques behind most of this aren't new, but we do have work to do to apply it to IoT. And the scale and the size of the problem, again, do present challenges, but that amount of data that's available does give us the opportunity to do robust, accurate clustering. So that's a good thing. And here's how we see this working. We call it the behavioral analysis 5-step. So step one, observe. So in theory, IoT security is pretty simple. You have a device that connects to its application that runs on a server somewhere in the cloud. They mutually authenticate each other and protect their communication with integrity, checking, encryption. But, this discussion ignores the fact that there's a network in between, and in some case, several networks in between, several networks in the middle of this. So think about a car connecting to its manufacturer. That car first connects to a mobile service provider, maybe two of them if the car is roaming, and then onto the internet, which also could be multiple service providers, until it finally reaches that manufacturer's application in a data center somewhere in a public cloud or private cloud. Now, these networks in the middle have little to no visibility into the identity of the IoT device, the IoT application, their intended uses or behaviors. So step two, we need to monitor the device behavior. Still at step one, need to monitor the device behavior. Who is the device communicating to? how often, how much, what are the packet and flow characteristics. And then we get on to step 2, cluster similar devices. So cluster analysis will reveal the flocks, the categories of IoT devices that share these same behavioral characteristics. And this establishes the baseline normal behavior. So, is that dot in the upper right there part of this cluster? Now, cluster analysis by itself doesn't tell us exactly what those devices are. It just says those things are part of the same flock, the same category of device. Ultimately, we do need classification algorithms to classify the types of devices after we've clustered them. And domain expertise definitely is required to match observed behaviors with categories of IoT devices. An example, so you observe a particular device, it sits idle most of the time, gets an OS patch download from a public cloud maybe once every 2 months. Let's say an end user checks it over web interface once a week, et cetera, et cetera. Okay, maybe this device is a Nest thermostat or some other consumer device. Other examples, video cameras are going to stream pretty regular high data rate traffic. Sensors on the opposite end of the spectrum typically are going to transmit very small amounts of data. Many of these sensors do this very infrequently. So, Fitbits, HVAC systems, robotic arms, elevators, parking meters, whatever, all are going to exhibit different behaviors. Then on to step 3. Step 3 is detect anomalies. So once a device is part of a known flock, cluster analysis then reveals the normal versus the deviant behavior. So that red dot in the upper right, that device, it represents a device. What's going on there? So if you've ever been to Central California wine country, it's famous for wine, of course, but it's also famous for ostrich farms. And if you've been there or you've seen the movie Sideways, you know what I'm talking about. So a couple years ago, I was there, and I saw this ostrich doing this crazy dance, and I Googled it, and it turns out that this is actually normal behavior, and I can't remember if it was a mating dance or some male protecting his territory kind of dance, and you can Google it yourself. But I wouldn't know that this was not an anomaly without that domain expertise, in this case, a bird expert, via Google. But, if you saw, let's say, a seagull doing the same dance, then you'd know something was wrong. Now, back to networking, an interesting thing about networks is that the behavior of a network doesn't stay the same for long, and this is different from a lot of other machine learning use cases that you'll hear about out there. So let's take natural language processing, NLP, for example. Sure, a few new words might pop up here and there, but overall languages don't change that much, and certainly not over a period of days or weeks or even months, and barely even over years. But IoT devices, do appear and disappear on the network often, and existing ones can change their behavior from one day to the next. So think of a refrigerator that maybe has a microphone to monitor its compressor, and if it hears something wrong, it's going to make a repair call. And then one day it gets a software update that enables that microphone to also listen to voice commands. So this new functionality is going to alter its behavior from the perspective of the network. It's going to use a different session for that continuous audio stream for voice recognition. And it's generally tough to build and train these machine learning models based on errors and anomalies, because anomalies, by definition, are rare. So the only viable way to do it is to look for outliers and determine their causes and really go through this process that I'm talking about. And, of course, one of the big challenges here is to select the important and relevant IoT device behavioral characteristics that determine these clusters and then that determine the devices themselves, and in machine learning speak, the features of the model. So for example, temperature sensor isn't going to connect to a large number of servers or make repeated DNS requests. Parking meter, shouldn't have a Facebook account. Now, once we've determined the anomalies and detected them, then we go to step 4, identify the root cause. So this is where we figure out whether this anomaly is a security problem, is it accidental, is it malicious? Going back to the bird analogy, so birds acting strangely, is a tsunami coming or just a car driving by? Is it a wounded bird we're dealing with, or is it a cuckoo that's trying to fool us? And managing the false positives is almost as important as determining the true positives. We hear from the SecOps people all the time that they're overwhelmed by information. So the solution here is to zoom in on the problem for granular analysis. A lot of what you hear today is about local versus central processing. Juniper, for example, our advanced threat protection appliance, ATP appliance, can help out in the case of zooming in and local processing. But we definitely also need to aggregate and correlate data over time, geography, different network domains, to get that full picture. And a human expert has to perform this root cause analysis, at least initially, to build the model to figure out whether an unpredicted event is an anomaly or just a normal change in behavior of an existing device or a group of devices. And you can have one of two outcomes in this step. So A, if the anomaly turns out to be not malicious or not something to worry about, we stop here, update the baseline behavior of this category of IoT devices, tune, retrain the machine learning model to accommodate this observed behavior. Or B, if we determine that the anomaly is malicious or something to worry about, then we go to step 5. And step 5 is remediate, and this can come in different forms, from a more manual intervention with a human fully in the loop, or to something much more automated, like calling a Python script to rate limit, block a port, instantiate a new policy, reboot a line card, whatever. Juniper has a product, HealthBot, that monitors infrastructure and in some case gives you these automated remediation type responses of network problems that it observes. And you could see an evolution in this step where machine learning algorithms actually start to develop new scripts and apply to new situations that might arise. And then finally, when the problem is resolved, when the problem is fixed, you zoom back out to preserve resources and limit that amount of information that's going to the SecOps people. So that's just a quick laying out of the process at a high level. And, some of this, to be clear, I'm speaking about an ideal state that we're trying to get to. Definitely are challenges as Juniper works through this, and certainly we need help from others in the industry to really fully solve these problems. So I'll go over some of these. First, visibility. I mentioned before that a lot of IoT data is encrypted, certainly with narrowband IoT, Sigfox. Devices are often hidden behind firewalls, behind IoT gateways. They might be on non-IP LANs. And again, this is why behavioral analysis, this cluster analysis, is critical. We can't always see that device and directly identify it on the network. So we need more telemetry and visibility than firewalls alone can provide. Another challenge, data. So networks produce mountains of data. You need to find a balance between local and global processing. So local processing, for example, at an IoT gateway in the edge, saves bandwidth, it's faster, isolates threats faster. And then global views, processing aggregated data, all else being equal, is going to provide better context, better answers, to be honest. There's a couple of issues with respect to data that we actually have working in our favor. Unlike a lot of machine learning problems today, first of all, we have no shortage of data to actually build and train the models, which is nice. And second, a problem that we don't have, most network data is actually pretty well structured. It's time stamped, has an IP address, so there is metadata associated with this network data that we collect. But one problem with the data is that it does need to be labeled in machine learning speak, and that means we have to tie the outcome or the root cause analysis in the context of what I was going over to that observed behavior to cluster the device and eventually to classify that IoT device. And this requires a lot of work, plenty of human expertise. Again, initially at least to build the models out. Another ongoing challenge. The arms race, certainly is always a challenge in the security world. The bad guys are always trying to fool the algorithms and, trying to learn to blend in with the flock. And then finally, skill sets, so programming, data science, machine learning expertise. As we get further down the road into prediction and closed loop automated remediation, we need to continue to merge the worlds of networking and machine learning to build the right models. Now, from the Juniper perspective, our overall strategy is defense in depth, pervasive security integrated with the network. We no longer see a distinction between networking and security, and here's an example of what I mean by that. So, I mentioned before, we need telemetry from all network elements to solve the IoT security problem. So routers and switches are a key part of this solution, not just firewalls, and so we're correlating the data from all of those sources to help figure out what's going on, and that's what you need to do. In a general sense, Juniper continues to build foundational security technologies in many areas. We natively integrate security with our SD-WAN solution and with our Contrail orchestration solution. I'm starting to think that people don't understand what the word native means. You're hearing it thrown out a lot. If you start with legacy code written for the physical world and then containerize it, for example, you can't call that cloud native. Or in this case, if you add security onto some legacy existing solution, then that's not natively built for security. So that's not what we're talking about here. But enough of that rant. Back to a couple more points about IoT security. Juniper, we're also working with the cloud hyperscalers and other IoT solution vendors to integrate their IoT solutions with our infrastructure. We're working with application vendors to better identify IoT devices. So again, to be clear, we're not suggesting that behavioral analysis is the only way to solve the IoT security problem. It's not an either or. You do need the traditional methods like threat signatures loaded on firewalls, as well as the newer machine learning techniques. In some respects, Juniper is known for big routers and the fastest firewalls, and this is all true. But on the other end of the spectrum, we were the first company to offer a containerized firewall, and that's our CSRX. We've deployed this now on lightweight ARM processors for connected vehicle applications, for example. And then finally, over top of all these solutions, we have a management and orchestration layer. And this is how I started the presentation. Simplifying network operations is always the goal here. So that's it. Thanks for listening. A final thought I want to leave you with, and maybe I'll have time for a question or two, is that the network has been seen as a liability with respect to security, but Juniper views it as an asset. Okay, so let me see what questions are going on? Okay, I hope for that one speaker I got to the point quick enough. Okay. I don't see any questions here, but one question I did get before I was live. What Juniper products are we talking about here? So what I went over, some of this is ongoing work we're working with our customers on. I wouldn't say we have an exact product that maps directly to this 5-step process, but a bunch of different areas to talk about. We do have a bunch of machine learning capabilities, and some of this we've acquired, some of this we've developed organically. We just bought a Wi-Fi company, Mist, and Mist is a great Wi-Fi solution. And in particular, it optimizes the Wi-Fi user experience, and it does this by monitoring a bunch of variables, predicting trouble spots, and preemptively fixing any problems before they occur. Our AppFormix line of tools is about monitoring network infrastructure and, again, using machine learning to predict failures that might be about to occur. So AppFormix, and we have a series of bots. Our health bot, for example, uses these templates, and we call them playbooks. And we have predefined playbooks, or you can build your own. And these playbooks automatically remediate problems that come up. So you can look at things like VPN health, black hole detection. And then a final area, throughout our security portfolio, I don't think you can separate analytics from security. So, in some cases, all the way at the low end, I'll say, simple regression models, which have been a part of malware detection solutions for a long time, but also getting into classification algorithms and other behavioral analysis. Our Sky ATP product is really good there. One last thing to say about IoT security. So the 3GPP best standard, I don't know if that's finalized and launched yet, but when it is, our firewalls will certainly support that. And you can go to juniper.net for more info. Let's see if there's one more question here. Okay, where can we get more info? Give you 2 ways, or maybe 3. So you can go to juniper.net. And, honestly, just Google Juniper plus some of the topics I was talking about today, and you'll get from it some info. Also, please feel free to just email me directly, and I can either answer your question or point you to the right place. And my email is benbaker@juniper.net. And I hope the bots aren't so good these days that they can pick up my audio and start spamming me based on that email, but crossing my fingers. So that's it. I'll wrap up here. Thanks again for listening, and good luck to everyone in helping to solve the IoT security problem.